All right. So, I did good. I promised, I don't know how much commitment I made to it. Here's the formula sheet. It's very small. There's actually not that many equations that we're going to be using on this test one. Here they are. It's the kinematics equations, and then a little bit of stuff with force, and then a little bit of stuff with circular motion, and there's a gravitational constant, right? Gravitational. Here is the acceleration due to gravity. Gravitational constant is actually a different thing. It's really not that much. So, at any point, so like I do not have SOHCAHTOA up here. I do not have the Pythagorean zero up here. I do not have unit conversions up here. I do not have how to find the x component because again, oh, and I'll post this, y'all. I'll post this onto web courses. Anything I show you all in class, I will post so that way you have access to it. Okay, feel free to take pictures of all that stuff. But I will post this document after the end of class today. I mean, you can see what I have, and obviously I don't have everything else. But next week, so we only have this week and next week, and then it's test week. So we got 2 weeks of stuff left to cover. This week's stuff won't be bad. Next week's stuff, we're doing forces, and that's going to be, there is going to be some like, I don't want to say challenging, but like on par with maybe kind of 2D kinematics in terms of difficulty, a little bit anyway. Make certain you are staying up to date on things. If we just kind of look at our calendar, so a reminder to you all, we have this week, next week, and then the exam is on Wednesday and Friday. The Wednesday will be the multiple choice part of the exam. Friday will be the free response. Wednesday will be 20 questions. I've already made the questions. I just need to proofread them, check them, make certain the time, I'm pretty set on them at this point though. And then Fridays, I'm going to give you 3 questions, 3 free response questions. You will get to choose 2 out of 3 of those to solve, and those will be obviously more involved problems. They will follow this rubric here. So this rubric here, notice it's only, so the free response questions will be worth 40 points. The multiple, again, I will put this all in an email. I'll put this in an announcement so it's in writing, so you have all the details, what to expect. 60% of the grade will be multiple choice. 40% of the grade will be free response. So 2 questions, each worth 20 points from that. Notice that this rubric only goes up to 10 points. That's because each question has 2 parts, each part being worth 10 points. Okay? So, each part of the question will be evaluated as follows, and it follows the 4-step problem-solving process. You get a few points if you drew an accurate picture and you identified the givens. You get a few more points if you got the, what are you solving for? You get a few more points if you got the right equations. You get a few more points if you set up the problem with the numbers in it correct, like you did the algebra right. And you get all the points if your final answer is correct. So at the end of the day, if your final answer is correct, you're good to go. Now, to that end, I will warn you there will be slightly different versions amongst you all. So if you write the wrong answer from someone else's, ain't gonna do you much good. Yeah.
I see that 10 points for like full points.
Yeah, because there's going to be 2, each question will have 2 parts, each worth 10 points. Yeah, it's a good question. Each question will have 2 parts, each worth 10 points. So 10 plus 10, 20, 2 questions, 20 plus 20, 40.
Will we be needing a Scantron on the data?
You will not need a Scantron. I prefer, there's something called ZipGrade where basically I make the Scantron for you all. So the Scantron will be stapled to your all's test. You'll bubble in the things, I will collect it. I will be able to scan those with my phone. I like it a lot because it lets me get the responses quickly and also do a few other things. So I will provide the Scantron to you all. The only thing you will need to bring to this test, so next week I will bring 3x5 note cards. So one of the things I mentioned you way back, during the test, I will let you use a 3x5 note card with anything you want on it front and back. Obviously, you can't staple a bunch of sheets of extra paper to it. But if you want, you can type stuff up, print that out, and like glue it to it. I mean, you can tape it down too. I just don't want a bunch of loose, it doesn't count as one note card if you stapled a whole bunch of extra papers to it. So, Again, I will send out these details in an announcement to clarify it all. But 3x5 note card, front and back, I do not care what you want. I do not care what you put on it. I don't recommend wasting space on the equipment. I will give you all this on the test. So I don't recommend wasting space on this. But if there's certain things that are helpful to you, like how to get the vectors, how to the unit conversions, what variables go with what. If there's anything that you think you'd like, put it on there. You can write it as small as you want. I don't care. At the end of the day, physics is not about memorization. Physics is about, do you know how to solve the problem? Do you know how to think through the problems? Do you know the concepts? And honestly, again, either you're ready for it, the Scantron ain't going to magically fix. So, anyway, put whatever you want on it. I don't care. It's kind of my way of giving you all something to also study with. It's kind of nice. Also gives you all a bit more confidence going into it and stuff like that, which can just reduce some stress and things like that. So, again, I will send out the details. I will post this. I will send out an email tomorrow with all the details of everything I just said in writing, so you all know what to expect. The first test in any class is always not fun because you don't quite know how it's going to go. You don't know how to study for this, y'all. Go through the problem sets. Go through the quizzes. That's how you study for this. Go through the clicker questions too. Clicker questions, quizzes, and problem sets. Look through those things. Don't look at it with the worked out, look at it, you can look at it with the answer. Don't look at it with all the math done. Make certain you can figure out the math without seeing the solution, because that's how the test is going to be. Yeah?
Are some of these stuff that we haven't gone over yet?
Yes, yeah. I haven't taught you all about forces. That's going to happen this week.
Okay.
The only things we've covered so far is this first chunk. This bottom chunk is what we're going to cover these two today, hopefully. Should be, we'll get to them, maybe we'll roll into Wednesday. And then we're going to cover these the next week and a half or so, yeah. I'm going to warn you all, we're going to have new content all the way up until Friday of next week. And then, yeah, we'll have that kind of buffer till Wednesdays when the test begins. Monday will be a review day. If I need to, hopefully we won't need to cover anything new on Monday, shouldn't need to. Hopefully Monday is just me solving problems. Yeah, that's that. So, there you go, y'all. Make sure you're staying on top of things, because especially, again, I'm also going to warn you of this. So next week, we're going to finish covering the forces. You will have a quiz due that the Saturday of the test week. So you're going to obviously want to do that quiz before the test. So this last gets a little bit crammed in there. That's just how it goes. You need to make certain, especially this week before the test week, that you're staying on top of that stuff and trying to solve it throughout it. Because, yeah, you kind of get the weekend, you get a couple days, but while you'll have all the way to Saturday, I highly recommend not doing the quiz after the test. The quiz is to make certain you're ready for the test. You're welcome to do the quiz after the test. That is perfectly fine. But at least do one of your attempts before the test days, because remember, the quizzes are good indications of what kind of things you need to know for the test. The quizzes are to help you all track your understanding. You want to know if you understand forces before I test you on whether you understand forces. Okay? So, anyway, there's that. Okay, so last class, and again, I'll send out an announcement and then we'll have more time for more questions on this, but that was a lot at once. There was make certain you all download the newest version of the problem sets. There was one small mistake on number 10. One part of it was off, so I've uploaded that. Last class, though, we were doing two-dimensional motion. And I started to solve a problem, so I'm going to finish that problem, hopefully solve one more, and then we'll talk about circular motion today. So we'll finish up 2D kinematics today, we'll get into circular motion, and then the rest of the week will be Newton's laws, circular motion, Newton's laws, and then next week is more force problems, aka kind of, we're going to learn that Newton's laws all have to do with forces, and so that's what we're spending the next kind of 2 weeks on, this week and next week. But yeah, 2D motion, y'all. Projectile motion. Make certain you can do projectile motion. I'm going to finish up a problem today, but these are kind of critical problems. So, we ended last class with this plane that was going horizontally. It dropped something at 800 meters, and we're basically trying to figure out how far the thing travels. We wrote down all our givens. We identified that time. What limits the time? The y component. The y component is going to limit the time. Once we find the time in the y component, we will then use that in the x component to get how far it's going to go. So that's where we left off, was with that step 3 what equations to use. Okay, and we're going to use this guy right here, yf equals y naught plus b naught yt plus 1/2 a yt to find the time. So, now normally I tell you all, well, and this is kind of true here, we'll do the algebra with the variables. So, my final y height is going to be 0, so we'll end up plugging that in, find whatever that there. This term's going to go away. That's just what I want to point out now before I do any algebra. The initial y velocity is 0. The way to think about components of velocities in the beginning, is it going up or down at all? It is not. It is only going left, right. So there is no y component of the initial velocity. So, if we kind of take this and then rearrange it, we get delta y, actually negative, no, delta y is good. Let's see, delta y equals 1/2 at squared. And if we rearrange for time, we find the following. T equals square root of 2 delta y over a. You just rearrange that, multiply the 2 over, divide by a. And that gives us the time for something falling. So that's kind of nice. Now, these little kind of equations that kind of pop up in things, these are useful. You just have to be careful to make certain it's applicable to the problem you're solving. Sometimes the little equations we have are good for this type of problem, but not good for other types of problems. So just don't get in the mindset that any equation, anytime we come up with something like this applies to every single type of problem. It's always safe to start with the kinematics and then just kind of derive what you need. Okay, so step 4, we'll kind of chuck this in here. So t equals 2, and I'm actually going to point out something here. A is negative 9.8. We cannot take the square root of a negative number. I mean, technically you can, you get imaginary. At this stage of your all's math, physics stuff, imaginary numbers should not happen. At some point they may. Now, how do we get rid of that negative? We think of this problem. Our final height is 0. Our initial height is 800. 0 minus 800 is negative 800. So the negatives cancel out. Everything works out. It should work out. So we get a time of a number. Square root of that thing times that. Alright, so square root of, and we can just cancel out. You don't need to plug in the negatives in your calculator if you know they cancel out. We get a time of 12.78 seconds. We think to ourselves, does that make sense? Always a question you should ask. 12.8 seconds, that's a long time, y'all. 1, 2, 3. You get the idea. That's a long time. It may not seem like a long time, but for something falling, that's a long time. But it's almost a kilometer up in the sky. 800 meters is almost 1 kilometer. So that's a long time, but that's a large distance, so that's okay. All right, and our last step, y'all, is the easiest one. Delta x equals, we know the time, we know my x velocity, so we're just going to plug that in and kind of cram it in here. I'll shrink some things so I have room for the final answer. It's a little messy here, and in general, I recommend you all give yourself more room to solve these things. I'm not doing a good modeling here of that, but it just almost fits so nicely that at the end of the day, this problem didn't even ask for the time, but you have to find it. I can basically guarantee you all, any projectile motion problem, it is useful to find time. You can almost guarantee that you're going to have to find time with solving these problems. It's the only variable that extends across x and y. And bam, there's our final answer, 1,775.01. If that's tricky to see, good news, it should be one of the answers in the problem set. So, it's also written in the problem set for number 7. All right, and it all revolved around x and y are separate, time was the limit, and the y direction, time was the limiting factor. Because it's falling, found time, plugged it into the x, called it a day. All right, these problems have a lot of steps. They have a lot of steps, and they have tricks. There are certain things you have to remember. or at least you don't have to, but it's going to make you may need to, but it's going to definitely make your life easier. Remember, there's a few things. If you toss something upwards, its initial y velocity will be equal to its final y velocity, just negative. That's something that comes into play. The time to the top is the same as the time back down to the starting height. The starting height. Now, if it goes lower, it gets wonkier. The time, the velocity in the y direction at the highest point is 0. That's not going to show up in this problem per se, but these are just the things. All the things we talked about for tossing something up in the air also apply to this. Also apply to these problems. So, we'll do one more, kind of set it up. I may not spend all the time solving it. Oh yeah, love this one. A projectile is launched at an angle of 30 degrees and lands 20 seconds later at the same height. So this is the one that had a slight typo, actually. Part D, the x displacement was a little off. So I'll kind of talk through this one. I am actually not going to solve this one in front. I'll show the setup for it and the thoughts you need. But for the sake of time, I'm going to let you all kind of work through it. I would love to spend more time on it, but we got to keep the ball moving. But I will talk about the tricks and tips that you need to solve this. So, we draw a picture. Always draw a picture. Always for these problems. So it launches with 30 degrees and it lands, at some point at the same height, and it takes 20 seconds to travel. The first question says, so we really don't have much here, y'all. We have theta is 30 degrees. We have the total time is 20 seconds. You know what? We're going to even put that little total next to that. The total time. Because there's all different times you can work with. Time to the top. Total time. At the last part just says 15 seconds. There's all sorts of times, so it's good to kind of label that T total, T tot. And literally the only other thing we know is that the gravity is 9.8 meters per second squared. That's it. And from just this tiny piece of information, we can find everything. But there's some clever tricks that we may need to remember that help us out. So we are trying to find this initial velocity. Not the x component, not the y component of it, the total initial velocity. We are trying to find the maximum height. We'll just call it y max. We are trying to find the range. That is delta x. I guess total, like the total displacement. If we kind of draw that on our picture here. We are trying to find this delta x. We are trying to find this this y max. Guess you could call it delta y if you really wanted to. We are trying to find part D, the displacement at a certain time, whatever. Okay. If we look at our kinematics equations as is, there is no equation that's going to let you find things with just what we've written down. So let me, let's look at our formula sheet. How nice. So let's see here. Remember, we're going to look in the x and the y component. First question that should come to your mind when you're solving these, what's the limiter for time? We see time here. What's the limiting? Is it the y component or the x component? Is it hitting a wall or is it hitting the floor? It's hitting the floor, so we should be working in the y component because we have this time, so immediately we should say, okay, we're going to do something in the y component. What are we going to do? We look at our equations. And again, I'm going to straight up tell you, none of these are going to work unless we figure out a couple extra pieces of information. I mean, we can do this problem a few ways, actually. There's a few things we know. Let's actually jot down what we know about this type of problem. We know that the initial velocity equals the final velocity. We know that with and this is maybe important. We know that our initial y velocity equals our final y velocity with a negative sign in front of either one of these. Remember, however, if something returns to the same height, very critical there. If it goes down lower, doesn't work. If it goes above it higher, doesn't work. But if it returns the same height, however fast you toss it up, returns back to your hand, the same velocity, just right back down. At the end of the day, a projectile motion problem, when it returns to the same height, it's just a free fall problem, something getting tossed up in the air, mixed with a constant velocity in the x problem, and they're just together at the same time. So we know that. We know a few other things. We know that the time to the top equals half the time t total divided by 2. The time to the highest point, the time to this, is half of the total time because of that symmetry. It returns to the same point. Same thing. If I toss something straight up, the time to the top is the same as the time to the bottom. So time to the top plus time to the bottom equals the total time. All right, one more thing we know. We know that the velocity at the highest point, so Vy at the top, so the velocity in the y at the top is 0. Okay? Again, there's lots of things we know about these projectile motion problems that help us. Okay, so I just kind of chucked all those there. That's kind of extra information. How does this help us solve the problem? Again, I'm going to give you all some tips. This is one that you really want to work through. And these tips are kind of here. See if you can solve this without having these tips blatantly in front of your face, and then come and view these when you get stumped. So, for solving the initial speed, again, we're going to be working the y component. If we can get the y component, everything's going to turn out great. Let's check out this first equation. The final velocity in the y equals final velocity in the whatever direction. Let's just say y equals initial velocity in the y plus a times t. You may wonder how that's going to be useful to you. The final velocity in the y equals the initial velocity in the y plus a times t. We know a. We know t. We also know that the final velocity in the y is negative of the initial velocity in the y. So if we take this and chuck it in there, we can say that that negative initial y equals velocity y plus at. That therefore tells us that negative, if we subtract that over, then we can solve for the initial y velocity. But how do we set that up? We had to know that the initial y velocity is equal to the negative y velocity. You have to kind of, again, I guess you could say this is memorization on some level, but trust me, you do enough of these problems. Look, my memory sucks. So honestly, if it was just memorization, like memorizing a bunch of history facts, I would have had a terrible time at physics. What this is kind of visualizing, understanding these things. If you can understand kind of conceptually, for whatever reason, that helps me remember. I don't know if it'll help you remember, hopefully it will. But the idea that this going up is the same as it going down, at some point that will start to just make sense. And when things make sense, they just kind of get easier to remember. So anyway, great. We can solve for the y component of velocity. Once you have that y component of the velocity, you have an angle, you have a side of the triangle. You can do the SOHCAHTOA to find this side. Great, and that'll be our initial velocity. And honestly, the farther we get in this problem, the easier it gets. The more pieces of the puzzle we get, the easier it gets. The beginning is hard. All right, what's the maximum altitude? What's the highest point it reaches? You need to know that the velocity at the top is 0. You need to know that the time to the top is half of the total time. Using that piece of information, you'll know final velocity. You'll know the time. You'll know the acceleration. You'll know the initial velocity. And you kind of got a whole bunch of choices of equations you can use to solve that. But this is the part that kind of unlocks what you're able to do, is understanding what's going on in a projectile motion problem. So this problem is great. This problem is great. But yeah, these problems, y'all, every single one of these you should solve. This one is a real doozy. But if you can do this one, so this is harder than what I'm going to ask you. Straight up tell you that. I'm not going to ask you a question that's hard on the test. But I really like this problem because I asked you all the question. Remember, time is limited by either hitting the wall or hitting the floor. This problem, you don't actually know what's going to happen, and you have to figure out which one's going to happen first. Is this person going to hit the wall, or is this person going to hit the floor? How do you figure that out? Do both of them. And whatever time is lower, that's the one that's going to happen. If the time to the wall is lower than the time to the floor, he's going to hit the wall first. If the time to the floor, or time to this is longer than that, then it ain't going to happen and you're fine. So anyway, you have to work through these problems, y'all. Work together. Because these problems have a lot of steps. This is kind of these problems have a lot of complexity to them, and they make you think through what's going on. So work together. Because when you're stumped, the hope is that someone else in your group, maybe they know the next step, and then maybe when they're stumped in the next step, you know the next step. And you can kind of, those little tricks, those little things you got to remember, people can help you out, and the more you practice them, the better off you are. But yeah. Work through every single one from this week, y'all. If you skip a single one, if you know how to do it, great, then it's easy. If you don't know how to do it, you should definitely do all of them. So either way, there's kind of not a great argument not to do them. So try them out. Again, here's that one. Just really good problem. There is a couple shortcut equations, but you have to be careful with these. You can straight up put these on your on your little 3x5 note card. Every single one of these assumes you land at the same height that you start at. There is problems where you do not start at the same height that you land at. So these only work if you start at the same height you land at, okay? Very important. That's where these ones come from. They're not on the formula sheet because honestly, if I put them there, they'll probably get used incorrectly. If I say, I don't know, there is a problem here, for example. This is a great problem to do. I threw a rock off a cliff. This is the difficulty level that I want you to be able to solve. I throw something off a cliff that is a certain height at a certain angle, and it asks you to find all the things. This is a fantastic problem to work through. This test, do you understand all the pieces? The one we I really like because it makes you rearrange things and figure out stuff. But anyway, work through these, y'all. It's good stuff. They're little puzzles. It's fun. I don't know. I'm biased. Obviously, I enjoy the stuff. I did a lot of physics. I enjoy it. But if you're in engineering, some aspect of this should resonate with you. This whole puzzle and figuring out things. You're going to be doing a lot of it in life. And it gets more enjoyable the better you get at it, like most things in life. So anyway, there's that. Try it out, y'all. Let's learn about circles. So it really wasn't mine. Let's go ahead and save this. So, this week we're getting into forces. We've been talking, we're going to start with circle stuff first because we got to cover circles. We've been spending all this time talking about things moving. The next 2 weeks are why do things move? How do you get something moving? Which sounds obvious, you push it. But what is a push? And coming up with a scientific jargon that we need to know to be capable of solving this. So, on to week 4, and we should be able to catch up because even if we roll into next circular motion, Newton's laws, this week will actually be pretty tame, which will great. Give you all some extra time to kind of do the 2D stuff. Next week is going to be back at it again, putting pieces together. Okay. So, circular motion, Newton's laws. We're going to talk about things going in a circle, position, velocity, acceleration. But then going in a circle. Talk about centrifugal acceleration and tangential acceleration. And then the last 3 points are really important. What is a force? How do forces affect things based on mass and acceleration? And how to draw a free body diagram. That's going to be a name that we're going to be using a lot in this very, very important skill. So, it's going to be great. It's going to be so much fun. All right. So, circular motion, it's exactly what you expect. It's things going in circles. Now, these things can be going in horizontal circles, vertical circles, all the circles. Yeah, and it plays into a lot. Anything that spins counts as circular motion. Easy example of that. You are on the earth. The earth is spinning. Therefore, you are making a circle. If you traced out the path of you on the earth, it's a circle. and everything else attached to it as well. So, here are some conditions for uniform circular motion, i.e. the types of problems I'm going to give you. The tangential speed is constant, meaning it's rotating at the same rate. For the stuff that we're doing today, it's rotating at the same rate. At the very end of this class, like the last 2-3 weeks, they're going to start speeding up and slowing down. But for now, nice and simple. Constant RPM. It's not spinning faster, it's not spinning slower, nice constant rate. We're going to learn about the second point. It's going to be a really important one. A body moving on a circular trajectory with constant speed is accelerated towards the center. We'll spend more time on that at some point later, but this is one this is probably one of the most confusing parts of the whole thing, is that the acceleration is towards the center. So we'll talk about that. Yeah, go for it. What's up?
Sounds like gravity.
It is like gravity. In some ways. Gravity is towards the center. We're going to learn that we can equate the force due to gravity equal to one of the equations we talk about today. Gosh, do I have a string or something? I'll have to borrow my duck that's attached to a string. I'll bring it Wednesday. It'll be great. So this is specific, anything like a roller coaster going in a circle, or you going in your car around a circle, anything going in a circle. And the tangential acceleration is going to be 0, meaning again, same thing as this. It's not speeding up or slowing down. Okay, nothing critical, like everything here is going to show up in the later slides. This is just kind of some foundational, like what are we actually talking about? Okay. Very important, we know clockwise and counterclockwise sounds silly, but I have no idea how to describe which way something's rotating without clockwise or counterclockwise. Case in point. This one here is clockwise, it's the direction a clock goes. This one's counterclockwise, direction opposite clock goes. Sounds silly, but I wonder if in 20 years, analog clocks, who knows if they'll ever get kind of removed and everything will be digital. I have no idea. But this could be like at some point, 50 years from now, talking to if you have children or grandchildren, just talking to young kids who are like, why is it called clockwise or counterclockwise? And you're just like, well, back in my day, Sonny, we had clocks that moved. I don't know. It's just fun. Maybe. Who knows? Probably not. People like clocks. But I have no other way how to describe this. You can't say that this thing is spinning to the right, because I could easily have drawn the arrow down there and it's to the left. So you can't just say it's spinning to the right, because on the bottom it's spinning to the left. Same thing with this one. This one's spinning to the right on the bottom, but it's spinning. So anywho, that's what we got. You got to know clockwise and counterclockwise. Very straightforward, but it's important. Okay. Also important that we know angles can be measured in different ways. There is degrees, which is real nice, but you will find as time goes on, radians are mathematically superior, which sounds kind of pretentious and silly. I say mathematically superior. Pi is not a nice number, 3.1415. Like it's a bit of a mouthful. And so it's a little funky there. But when it comes to equations, we're going to find with circular motion that you have to use radians for some things. And I'm going to straight off, like from the get-go, we're going to see some examples of why we have to use radians for some things. Radians are actually a better description of angle. Again, that sounds silly, but you'll see. You'll see why it's more useful to us physically. So let's see what you all know about radians. How many radians is 45 degrees? Again, it has been so long since I've been where you all are at. I learned radians at some point. I do not remember where I learned it. It may have been my physics class. It may have been my calculus class. So I have no idea if you all have actually learned radians. I think you have. I hope you have. Like, I'm pretty sure you would have at some point. I don't know if that was calculus. I don't know if that was trigonometry. I don't know what it was. But let's see. How many radians is 45 degrees? Is it pi over 4, pi, 2 pi, or pi over 8? Oh, look at that. Okay, great. You all do know radians. All right. We'll go to 40 seconds just to give the online people some time to actually see it pop up. Did they do this in calculus?
Trigonometry.
Trigonometry was the main one. Calculus as well? Okay. Again, I don't remember. 5, 4, 3, 2, 1. All right, so here's the key to how you kind of, the answer is, you know, just, I guess if you got to memorize, it's this. But honestly, here's the way my brain does, let's see. Okay, it's on the next slide. Here's how my brain does it. How many radians are in a circle? 2 pi. How many degrees are in a circle? 360. And then I just kind of figure out the ratios. Like, legit, I don't have these things memorized. I know there's 360 degrees. I've got that memorized. 45 is an eighth of 360. Pi over 4 is an eighth of 2 pi. That's I kind of break it down into pieces and whatever. Do whatever you need to do to remember this. Here's the conversion in mathiness, which honestly is harder than you just take the 2 pi, you multiply, again, it's the ratio. It's literally what I kind of just logic through. If you know there's 360 degrees in a circle, and you know there's 2 pi radians in a circle, 180 degrees, that's half of 360. What's half of 2 pi? Pi. That's kind of how I logic through it in my brain, so I don't have to remember. I don't have that memorized. But all math is a representation of logic, and if you know the logic, you can make the math. So, anywho, ratios. All right, why use radians? Great, there it is. Arc length is one of the reasons. Arc length, if you want to figure out the distance on a circle, not the whole circle, just a piece of it, all you do is take the angle and you multiply it by the radius. If you use degrees, this doesn't work. Radians, this works. And I'll give you all a very easy, well actually I'll let you all figure out the easy example of this. Why is this true? How can you prove this to yourself? We'll do a couple problems that'll kind of like prove it to yourself that this is true. It's such a simple equation. Just take the radius, multiply it by the angle in radians, and you will get the distance of this arc. So if I have something that's, you know, pi over 4 radians, multiply that, if my radius is 5 meters, pi over 4 times 5, bam, that's the length of that arc. It's so nice. Super simple. You cannot do this with degrees. Degrees don't work with this. Radians are literally defined from this stuff. That's where radians come from. They weren't just made up. They come from this relationship. Whereas degrees, why is it 360 degrees? That's like I don't know, someone just kind of made up that number. It's probably based on something, but I have no idea what it is. Mathematically, I have no idea why 360 was chosen. It feels, again, I'm sure there's a reason for it, but I don't know the mathematical reason if there is one. Just kind of like, yeah, I knew. All right, so let's logic it out, y'all. If you're walking on a circular path with radius r, what is the distance you travel? Notice I said distance, not displacement. What is the distance you travel after making half a revolution? So to draw a picture of this, here's a circle. I am asking for this, not displacement. Displacement would be just, hey, straight across, where you start, where you end. I'm asking for distance. Is it 2r, 2 pi r, or 360r? Or you know what? To really confuse some people, is it 180r? Ooh, did I add that because it's the right answer, or did I add it to confuse you? We'll find out. All right, we'll go to 115-ish. All right, in 5, 4, 3, 2, 1. Pow. All right, so we use our nice little equation. The arc length equals the radius times theta. What is my angle here? In radians, it's pi. Pi r. So yeah, I purposely put that one at the end just to, no, we don't use the angle in degrees. All right, let's take this full circle. Because you're making a full circle here. It's a good joke. I don't tell you all enough jokes. It sounds like, why would I do it? Let me read. If you're walking on a circular path with radius r, what is the distance you travel up to making one full revolution? So with my high school students, I usually have a joke of the day. Thankfully, I have today's memorized, but I'll try to bring them in. The joke for today's class was a plateau is the highest form of flattery. The plateau is a flat thing. It's good. It's good. I love them. Kids have a mixture of love and hate for them. All right. We'll go to 45. 5, 4, 3, 2, 1. All right. It's the circumference of a circle, y'all. This is why the circumference of a circle is 2 pi r. The equation that you've been told all your life, why is that? Because the arc length is defined as the angle times the radius. So again, radians, good stuff. That 2 pi literally comes from this. Comes from this. Half of this would be pi r. Quarter of this would be, that's where the equation actually came from, is 2 pi r. Pi, if you take a string and you measure it around. So radians come from a physical measurement, basically. Pi comes from this, that's how it was discovered, was this whole physical rate thing. So, okay. Now we're going to get back into physics, like this is kind of physics, measurements and all that. Let's just say I'm going in a circle, and it takes me a certain amount of time to go in that circle. How fast am I going around that circle? Well, the distance I travel is 2 pi r. The time it takes is t. We said that your velocity is the change in distance. We'll say x. Change in distance over change in time. How? That's how fast you're going in a circle. Distance divided by time. 2 pi r divided by t. How fast, how long does it take you? This t is the time for one revolution. Very important. So in fact, I should clarify that here. This time for one revolution. So in fact, I probably should have called it the period. Let's go ahead and fix that actually. Capital T. It's good to use the right notation for y'all. This is technically called the period. We're going to see this period thing more as the class goes on. But yeah, take the distance that you travel in one circle, divided by the time for one circle, and you have tangential velocity. Now, so the equation is fairly straightforward. 2 pi over t, not too bad. What is a little tricky is figuring out the direction of this. Now, in this circle I drew here, I didn't maybe make it clear, this thing's rotating counterclockwise. And so we're going to do a practice problem with this. The tangential velocity is the velocity tangent to the circle. Now, thankfully with you all, I could actually talk about the word tangent. With high school students, they haven't probably heard that word. But probably you all have heard tangent at some point. Tangent is the line that only touches one spot on the circle. So the tangent line, now the trick to doing it is the same I taught them. If I want the tangent velocity here, you draw that dot, you draw a little line, and then you make that line bigger in a straight line. So in this case, if it's counterclockwise, you got two options, either to the left or to the right, and you just think what makes sense. Which way is this thing traveling at the top? Boom. That's my tangent velocity. We can do the same thing down here. Tangent velocity here, draw a little line that's straight, make it bigger. So on and so forth. The tangent velocity, here's the way to think about tangential velocity. One, it's the direction of velocity at that point. At that spot, that's how fast it's going, and that's what direction it's going. Another way to think about this tangential velocity, if I was going in a circle, again, I'll bring my duck on a string tomorrow, I'll make a note of it or something. If I release this thing at this spot, it will fly in that direction in a straight line, assuming no gravity or anything else is affecting it. This is the direction it will fly if I let go of it at that spot. It will not make an arc. A lot of people think that if I let something go, for example here, we're ignoring gravity here, very important. I'm ignoring that no gravity. If I let this go, a lot of people think it's going to curve. And the question is, why would it curve? The second it lets go, it doesn't know that that circle exists anymore. The only thing keeping on the circle has been removed. So to that end, it doesn't know that that circle is still going on. It will just fly off forever and ever in a straight line, again, assuming no other force is acting on it. Okay, so let's put this in application. Let's find the direction. A ball is being swung counterclockwise. You know what, since I just showed you counterclockwise, let's mix it up. A ball is being swung clockwise. So we do have to remember the direction clocks go. What is the direction of the tangential velocity at the point shown below? Up, down, left, right. Notice, none of these answers are up with a curvy path or down with a curvy path. They are all just straight directions. Up, down, left, right. What direction is the velocity at this spot? All right, we'll go to 55. We'll go 10 more seconds. In 5, 4, 3, 2, 1. All right, so remember, first step. What the heck is clockwise? It's the direction a clock goes. All right, so then we do our little trick. We draw a little line. And then we say, is that line go left or right? Well, it's clockwise, so at the bottom it's going to kind of, fly off. So that is left. Let's see how we did. Oh, good, we got some different answers. But yeah, this is something you need to know. The direction it's going, just like everything we've done in this class, anytime we talk about vectors, and that velocity was a vector, as weird as that may seem. That velocity that we just talked about, that tangential velocity, anytime we talk about velocity, it's a vector. All right, weird. Let's see if I go to the next slide, if I'll fix things. All right, notice that this is hidden. You don't need to know this right now. I put this in here. This is hidden. I don't even know if it converts, so don't, this is not going to show up for a while. A little preview of things to come. Weeks from now. Anywho, so don't worry about it too much. It's here because I started to debate whether or not I should put it in here. But at the end of the day, decided, no, we're going to cover that later. So, this, not doing it right now. All right, but what keeps did it do the thing? Is it a ghost of, yep, all right. So what keeps in a circle? We'll just kind of knock out the rest of this. Any handwriting I do, we only got 3 minutes anyway. So just accept that ghost of a red mark is going to be there on every slide. But what keeps it in a circle? Well, velocity has magnitude and direction. So remember, velocity, not only does it matter how big it is, it matters what direction we're going. And we are going to learn later on in the slideshow, well, and we've kind of mentioned this, if the velocity is changing, we have a word for that. Acceleration. Even if the value is not changing, if the direction is changing, it is accelerating. Easy example of that. If I'm walking in the room to the right, and I turn towards you all, I stop moving to the right. My x component of velocity went from something to nothing. My y component of velocity went from nothing to something. So remember, when we talk about velocity, we have to think of it in components. When we talk about vectors, we have to think about it in components. And when this thing's rotating, its x and y component of velocity is changing every single time it moves. Easy example, well, again, if I draw on this, it's going to be very angry. On the right side, it's going up. On the top, it's going left. I went from having only y component to only having x component. And then it rotates, and it ended up having only y component again. So we call this the centripetal acceleration. The equation for it is vt squared over r. I'm not going to go through the derivation. It has to do with geometry. Very interesting thing to look up, but I'm not going to spend the time on it here. This equation does just come from geometry, kind of piecing out what happens when it moves a little bit. The key part here, why is it called centripetal? Because it's towards the center. Centripetal sounds like the word center. At all spots on this circle, the acceleration is towards the center. And again, when I bring the duck, that'll be made clear. If you are going in a circle, So like imagine I got a duck I got something on a string and spinning it around. The string is always pulling it down. Gravity, a good example of this. When you're orbiting the planet, acceleration is always towards the center. That's what's keeping it in a circle. Why do things orbit the planet? Because gravity pulls it towards the center. Yeah. Yes. Good. Well, okay. Yeah. This technically. Yeah. Good catch. That should be meters per second squared. Yep. Acceleration is always meters per second squared, regardless of the type.
So if your duck is in no gravity and you slow it down, will it go towards the sun?
Yeah, so fun fact, we'll learn about gravity at some point, but gravity is just out, when you're in orbit, it's just outrunning gravity. When you're in orbit around something, you are literally just outrunning the gravity pulling you down. That's what orbit is. If you launch a rocket straight up, it's going to fall right back down. You actually have to go sideways to outrun it. Anyway, I don't know if that, did that clarify your, is that what you, hey, come on down, I was like,
I knew that.
okay.
I'm trying to relate it to your duck.
Oh, yeah, I'll bring in the duck, yeah, we'll bring in the duck tomorrow, it'll be great. It's my big old yellow duck, demo duck, he's useful. All right, y'all, good luck with your two-dimensional motion stuff.